Hello and welcome to this video on why chemical reactions stop, or at least why there's a limited result. Have you ever wondered why, if you mix bicarbonate, soda and vinegar, the reaction comes to an end? Obviously, eventually the reagents finish reacting, but that's just one example. There are many other reactions that are far more complex, involving many different chemicals. When we look at these far more complex reactions, how exactly do they come to an end if not all the reagents have been used? The reason for this is because some of the reagents are essential for any of the other parts of the reaction to occur. These are the rate-limiting steps and are also known as the rate-determining step. This can either stop the reaction, reduce the output, or limit it to a maximum level. Depending on the availability and reaction of this chemical, you get a certain speed of product creation. Fundamentally, you can think of a reaction like two funnels. On one side you have the reagents, then in the middle the rate-limiting step, and then on the other side you have the products. To understand what is happening, you need to establish a rate-determining step or steps and the equilibrium point. In the first instance, we need to establish the rate-limiting step. That is, the step which prevents anything else from occurring without it. For example, if you have a two-molecule reaction to produce a third and final product, you need to have both of them available. If one is less than the other and it's a 1-to-1 ratio, you will always only be able to make as much as the smallest possible denominator. This means that if you have a fundamental requirement, if there is not enough of that present, you cannot do anything else. In a way, you can think of it as being like a recipe. If you have all the flour you could possibly need, but you have no milk or eggs, you can't make a cake no matter how much flour you have. If you only have enough eggs to make one cake, then you can only make one cake regardless of how much flour or milk you have. There is always going to be an ingredient that prevents you from making any more than that. And this is what the rate-limiting step is. This is why, with any chemical reaction, we can figure out which part of it is the rate-limiting step, and it's nearly always the core ingredient or core reagent that's going to lead to a reaction with others. For example, if you want to turn CO2 into something else, or carbon monoxide, CO, you need to have enough of that to react with other things. For example, if you're after making ammonia, well, you need nitrous or nitrous oxide or nitrous trioxide or something similar, along with other products. If you don't have the other products, you can't make ammonia. This, of course, has a rather large caveat, and that is, you either have a relatively fast reaction, and when that happens, you don't need to worry about much because it uses up everything in one go, or close enough to. In others, you have a steady state reaction, that is, the reaction occurs progressively over time. If you have either one of these situations, you still need to consider the limiting reagent, and that is what you would consider the rate-limiting step. Not all reactions are going to be dependent on this though, and that's the second slightly more complicated part of looking at this. The second element is the equilibrium point. That is where you have a balancing scale between what happens on the left side of the equation and the right side of the equation. If thinking of this as being like a balance, as the left side of the equation becomes lighter and the right side gets heavier, the reaction of the left side reduces, meaning you get less of the right side equation reaction happening. This is how you're going to determine how much of a product you're going to get from any given reaction. The overall process is going to be defined as how many molecules can react on the left-hand side to the right-hand side. If you find that the number of moles you have in your equation on the left-hand side is equal to the right-hand side, you can ignore what's happening here, because it's clear you converted everything. If, however, there are moles left over on the left-hand side that have not reacted to what's on the right-hand side, so the right-hand side has fewer molecules in the end, or moles of what you're dealing with, you know that something on the left has prevented it from happening, and this is generally due to something like an equilibrium reaction. That is, it's gotten to a point where it's no longer chemically favorable to try and generate the products of the reaction, and so it stops. Of these two possibilities, the first is kind of like a very energetic and positive person who just goes out of their life and does the best they can and tries to do everything, whereas the right-hand side is like someone who's eventually hit their midlife crisis and decided to give up. As you can see, a reaction is not just limited by the availability of reagents, it's also limited by intermediary products and by the ability to chemically favor or, in some cases, stall a reaction. And that leads to a given end result being limited, or in some cases, the reaction is purely limited by the availability of reagents. Once they're all used up, there is no more reaction. Other cases, you may get some of the reaction occurring, which then makes everything else unfavorable. And finally, the possibility that it's simply that you've run out of one of the necessary materials whilst everything else is in abundance. Thank you for watching this video. If you have found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions you have below.